So we have talked about what bias means. It's the bias of an estimator is the expected value of the difference between the estimator and the population parameter. Unbiasedness means that this expected value is zero, or in other words, the expected value of our estimator is equal to the population parameter. On the other hand, consistency is about sample size. And it's basically indicating that the sampling error that we have, each time we are getting a sample, we get some different values from the population parameter theta. So being consistent means that if you look at the probability that the difference between your estimator and theta, the absolute value of that, so this is like your deviation from the population parameter theta, the probability that it's going to is greater than some number, is large, is going to converge to zero. This probability converges to zero as n gets to infinity. So as the sample size gets larger and larger and larger, you're getting closer and closer to the actual population parameter. This is called consistency. For example, our estimator for max may not be consistent, or may be consistent. I don't know. I mean, it really depends on the maximum age in a population. Every time we get a sample, even if you increase your sample size, increasing sample size may indicate better, but the actual maximum number in that population, if it's not in any of your, if it's really an outlier, and if it's not in any of the samples you get, you will never be able to prove that each time you increase your sample size, you're getting closer. So that's an interesting, the reason I gave that estimator is it's an interesting example showing that we don't always get sums and averages. All right. But consistency means that in general, as the sample size gets larger, you get closer to the actual population parameter. Now, some other descriptive statistics. Median. Median is like the middle, the center value of a population. So we can also talk about population median, which is the value in which the CDF is equal to 0.5. Okay, this is for normal distribution, for example. They are the same thing. The mean and the median is the same thing for normal distribution because they are the normal distribution is symmetric. But this is not the same thing for example, exponential distribution. If you look at the exponential distribution mean, which is 1 over lambda, we'll see that the median, if you look at the CDF value of an exponential distribution where CDF is equal to 0.5, it will not necessarily be equal to 1 over lambda. When the distribution, the PDF probability density function of a distribution is skewed to one side, is not symmetric, mean and median, these two values are not necessarily equal. So median is the central value. So it's if you sort the numbers in your random variables, for example, the center one, the middle one is called the median. Sample median is usually indicated with this capital M hat to indicate. So this hat, as you can see, is most of the time is used to indicate that it's some statistics computed about for a sample. So sample median is that middle number, which means that half of the sample data points exceeds data points. Sometimes they are called observations. Okay, observations. When I sometimes say data point, it's our individual observations. So the elements, members of a sample, are called observations or data points. If half of the data points are above and half of them are below, that's the median. Or the population median is, as I said, the CDF 0.5, where the value that we attain, CDF of 0.5, is the population median. So if you look at this figure, again, this is from the book, you see that median is going to be equal to the population mean, when we have a symmetric distribution like this, when it's right skewed, which means that it goes all the way to infinity. It has a heavy tail on the right. When it's right skewed, the mean is going to be to the right of this median. So the area under the curve here is 0.5 to the left of the median. And to the right of the median, the area under the curve is again 0.5. But this center of this distribution, it's not the center, it's like the center of mass. If you remember, mean is like the center of gravity of this, because this goes all the way to infinity. If you take the averages, the mean tends to shift to the right of the median if you try to take this center of gravity, all right? So mean and median will not be equal. And one example, I will give you some concrete example on the exponential distribution, and you'll see why they're not equal in general. And if it's left skewed, by looking at these population, if we look at the estimates of these things on a sample, and we compute the sample average and sample median, and we see that they are different in the samples that we collect, we may also make some inferences about the population distribution, whether it's left skewed or right skewed. If the mean is smaller than if the sample mean is smaller than the sample median, we may say that, oh, maybe the population distribution is also like left skewed. Yeah, this isn't that concrete example. For population median, we solve for the CDF function, cumulative distribution function. We set it to 0.5, and we try to figure out what this m is. Let's try to do it for exponential distribution for some generic lambda. The lambda is the only parameter for an exponential distribution, right? So if you look at the cumulative CDF function of exponential, whatever value we are given here, it's 1 minus e to the minus lambda x. So fx is equal to 1 minus e to the minus lambda x. So we are looking for a particular x in which this is equal to 0.5. So which value of x gives me a CDF of 0.5? So we need to solve this equation. There are so for a generic lambda again, we are going to write this median in terms of lambda. If we solve this equation, the value of m in terms of lambda turns out to be ln2 divided by lambda, which is equal to ln2 is 0. So natural logarithm of 2 is equal to 0.6931. If you divide it by lambda, you get your population median. And if you remember the population mean, it was 1 over lambda, right? So they are different. The mean itself was 1 over lambda, which is larger than the mean. So it's to the right of, mean is to the right of the median in the case of exponential distribution, which means that the exponential distribution is right skewed. That's correct, right? It starts at 0 sharp. There are no negative values in exponential distribution because it's usually we use it to model waiting time. Waiting time cannot be negative. So it starts at 0, but it may go all the way to the infinity, and that it's right skewed. It's not symmetric. And you see here that its median is actually smaller than its mean. So this is how smaller it is. So that's what median is. Population median for discrete distributions is a little bit a shady area because for certain cases we may have, when we have values that are for example, if we take n is equal to 5, then it takes values between 0, 1, 2, 3, 4, 5. You'll see that the middle value, when you sort these values, there are six of those values, right? 0, 1, 2, 3, 4, 5, 6 of them, including 0. And which one is the center? The center actually will be anywhere between 2 and 3. So 0, 1, 2 is the first 3 values. 3, 4, 5 is the second half of the values. So the median is somewhere between 2 and 3. So any value between 2 and 3 could be, you can say 2.5 is the median, but since this is a discrete distribution, there's no value 2.5 actually. So you sometimes say 2 and 3 are the medians. You may say, you may use both of them to indicate, or any value between 2 and 3 is the median. You can also say that. And sometimes if when n is equal to 5 in this case, so in this case, for example, we're going to have less numbers, I think. So I think it should be, is this still like that? So 0, 1, 2. So we just changed the p here. But if you look at this, the same binomial distribution, so we can still have 0, 1, 2, 3, 4, 5. So, but here, so what are we missing in this second figure? Oh, the effects. In this case, again, we have these values. But if you look at the cumulative distribution 0.5, it just is again between these two things, but it's not in any of them. So sometimes if we try, since this is not a continuous function, the CDF of discrete distributions is not continuous. So we cannot continuously say, we cannot take the integral and say 0.5 of the population is to this side. So this is the value where fx is attained, and it may not have any root. Basically, this is saying, I don't want to confuse you with the slide. It's basically saying that for discrete distributions, it's sometimes between two values. And the sample median is really simple. You just sort the samples by using any sorting algorithm you like. And if the size of the sample n is odd, the median is the unique middle element in the sorted list. If n is even, median, again, you say it's any point between two middle elements, or you choose both of them and indicate as your median if n is an even number. By the way, in your you haven't taken algorithms class yet, right? But it's also possible to find the sample median in linear time. There's a Kate selection algorithm. Sometimes it's called the median of medians algorithm. It's very similar to quicksort, but by using buckets of 5 and finding the medians of those smaller 5 element buckets in all one time. It's possible to find, and the algorithm is really similar to quicksort. It's possible to get rid of 2/3 of the array each time you're looking for the median. So if you're interested in this, you may take a look at this algorithm. It's called median of medians algorithm to solve the problem of Kate selection. Kate selection is like an order statistic, and when k is equal to n over 2, we are looking for the middle element. So if you're looking for example, if you have 100 elements, the 50th element that you're looking for, when they were ordered, what is this 50th element in this list? It's possible to find that in linear time without actually sorting the samples. Okay, so as I said, if you're not going to cover that algorithm in this, so it's in this class, because that's an algorithms course to find that in more efficiently in linear time. But I also argue that it's more efficient because it's constant terms. Although it's linear asymptotically, the median of medians algorithm, practically it's like if you don't have more than 1 billion elements, using quicksort will probably be faster than median of medians. They will have the same complete. It has a really high constant in front of it. But just know that theoretically, asymptotically, it's possible to find an order statistics, the kth element, the median of a set is possible to do it in linear time without sorting the array. Okay, so this was just a side note. Now, quantiles, percentiles, and other quantiles are different order. These are all called order statistics of a sample. So when it's 0.5, or when we are talking about 50% of the population, that's the median. So more general versions of that, or different versions of that median, are called different, they are given different names. For example, if instead of looking at 0.5, half of the population, if you're looking for quarter of population, that's called those, if you divide the entire population into 4 regions, each of those regions are called quartiles, okay? A quartile, as the name implies, intuitively, it's like a quarter of the entire population. The first quartile is 25 percentile. So it means that CDF, what is the value that is in which the CDF is 0.25? Okay, when CDF is instead of FM 0.5, if you say F first quartile 0.25, the value that you attain 0.25 CDF is your first quartile. Second quartile is the same as the median. So there are 3 quartiles. Let me actually, instead of trying to do it with gestures, let me try to again use the whiteboard. All right, so if this is my entire population, so this, I divide it into quartiles like this. So this is 25 percentile, 50 percentile, and 75 percentile. And this is also the median. And this is sometimes called the first quartile, or Q1, Q2, and Q3. So these terms, Q1, Q2, Q3, are special terms to indicate the first quartile, second quartile, and the third quartile, which basically means that 75% of the population is below this value. By the way, when we are talking about Q1, Q2, Q3, or when we are talking about median or this percentile or quantile, their units are whatever the unit the random variable is. So when I say, for example, Q1 is equal to, for example, 60 kilograms, if these are the weights of some people in some city, when I say Q1 is 60 kilograms, it means that 25% of the population have weight less than or equal to 60 kilograms. Okay, as you can see, the unit of Q1 is the same as the whatever your random variable is. So we indicate them Q1 is equal to 60 kilograms, or 75 percentile is equal to 60 kilograms, means that 25% of the population has less than that. And Q is exactly equal to median. So when you say Q2, second quartile, is equal to, for example, 70 kilograms, this will be equal to the median. It means that 50% of the population has weight below this 70 kilograms, and 50% of them are above. Here also, this Q1 60 kilogram also means that 75% of the population are above 60 kilograms. Okay, so this is all, if 25 percentile is this way and 75 percentile is the other way. Another interesting thing is called the interquartile range. This is an interesting statistic about the sample, interquartile range. It's a range. Again, its unit is kilograms. It's the distance between the first quartile and the third quartile. So this one, sometimes indicated by IQ or IQR, not IQ. IQ is for something else, like, right? Intelligence quotient. So IQ, interquartile range, or IQR, indicates the distance between first quartile and the third quartile. So 50, it's like, again, it's about something about the range of a 50% of the population that are at the centers, 50% of the population around the mean. So when I say interquartile range is, for example, 20 kilograms, this is a range, okay? This is not this doesn't show the boundaries. When you say interquartile range is 20 kilograms, it means that, for example, if this was Q1 was 60, it means that Q3 is 80. Okay, so when Q3 is 80 kilograms, this 60 and 80, as you can see, they're like actual weights that we're talking about. Although the unit of this one is also kilograms, is the distance between first quartile and the third quartile. This interquartile range shows how dispersed these values are around the median. A smaller interquartile range means that 50% of the population are within this 20 kilograms range. Okay, the smaller the interquartile range means that almost half of your population is within this range. Okay, so this is the interquartile range is just a population. It's a sample statistic that we collect. All right, and the relationship between these quartiles, first, second, third quartile, if we just give different numbers to these 25, 50, 75, for example, sometimes we may talk about 10 percentile. That 10 percentile, it doesn't have a specific name, like it's not Q1, Q2, or Q3, it's just 10 percentile. And the percentile also has sometimes, if you see in some places, quantile, not so all these different terminologies, lots of names. It's maybe confusing at first, but so these two things, percentile and quantile, are two terms that are related to each other. This one is 100 times more than what a quantile is. So when you talk about 10 percentile, you're actually indicating 0.1 quantile. So 0. Quantile, when you're talking about quantiles, you give probabilities between 0 and 1. Quantile directly refers to the CDF, but percentile is like you convert those probabilities to percentages. In order to convert that probability to a percentage, you multiply it by 100, right? Therefore, 0.1 quantile multiplied by 100, it's your 10 percentile. And it's always like CDF, it shows how much of the population is smaller than you. So when you're at 99 percentile, it means 99% of the population are this side, okay? So it's like CDF, it shows how much of the population contains random values smaller than this. When you're at 99 percentile here, you don't indicate that you don't say you're at 1 percentile. Oh, actually, it's like not the inverse of the CDF. Oh yeah, actually, yeah. In terms of the function, it's like the inverse of, exactly. So we give the CDF function, it's like the inverse of CDF function, perfectly. So a better way to put it. So here, let me say to a CDF, for example, we give a value here, for example, CDF 30 kilograms. What is it? Okay, it gives us some value which says 0.2. So this means that 0.2, the probability to have weight 30 or less is 0.2, which means that also 20% of the population have 30 or less weight. So this quantile, when you're asked quantile, 0.2 quantile, we will be asking, what is the 0.2 quantile? The answer will be 30 to that, exactly like the inverse of the CDF function. Very good way to put it. So quantile is the inverse of the CDF. Percentile is 100 times the inverse of the CDF. And these special places, 25 percentile, 50 percentile, and 75 percentile, are called first, second, and third quartiles. The distance between first and third is called the interquartile range. One thing that is interesting about this interquartile range is that there's this heuristic, or just some it's not a rule that is written in stone, but there's this maybe tried and practiced way of saying 1.5 times the interquartile range gives us something. It tells us something, okay? So this is just who decided on 1.5? We don't know, okay? But it shows there's this rule to define outliers in a sample, okay? If you have a sample, if you collect some data, many of them are here, for example, and some data are here. If this is how your data looks like on the x-axis, it may be the case that the interquartile range, this may be your Q1, Q2, and Q3. There may be many points here. Okay, so 50% of your points, this is Q3, 50% of your points are in between these two things. So this distance becomes your interquartile range. Since it's the distance, you can multiply it with 1.5, you get a different distance. Now, there's a term called outlier. Outlier is a data point or an observation, which is like, you may think it's due to some error, or they are really exceptions in the population. People that are really tall, or people that are very old, or very young, or very short. So if this is like the height of some students in some university, there may be outliers. Okay, but when you're doing some averages and some averaging or some other populations, if you want to infer some population parameters from the sample, sometimes when we are computing these averages, we pre-process our sample and remove these outliers from the sample, because they are like extreme cases, which is going to change the way the average actually is. So one way to have determine the outliers is 1.5 interquartile distance IQR. 1 point IQR below Q1 if you have a data point smaller than Q1 minus 1.5 interquartile range, they may be outliers here on this side. And similarly, Q3 plus 1.5 interquartile range, that may be another threshold you set here. Okay, so these are your thresholds, and any data point, any observation outside these thresholds may be your outliers. And so why do we want to remove the outliers from the data? Let me give you an example. Imagine you want to find the averages of some trees in a region. Okay, average height of the trees. If many trees are like this, okay, so the median, for example, and there's one tree which is much higher than those trees. Okay, if I have 10 trees here with that height, and there's one tree with that height, when you try to estimate the population mean, maybe a lot of trees in this population also will be in this height. When you try to compute the X bar, this outlier here is going to make you overestimate the actual population mean mu by computing this X bar. If you include this outlier, let's call it XO, and compute the average, this single example here is going to make you overestimate mu. That's one of the reasons. Actually, in something like this, for example, the median, not the mu, the capital M hat, is not going to be affected by this outlier, right? I mean, there will be, it will just move, the order statistics is going to just move one to the left and to the right if you remove or keep this outlier in your list. So in other words, median, the statistic median is more robust to the existence of outliers in your sample. Median doesn't change much. It's going to still remain whatever the 50th element or whatever the 50th percentile range is. It's just including this here is just moving it one place to the left and right, which means that it's almost at the same place. But averages are affected in a worse manner. Having this very tall tree among these other trees, it will because if in general there are all the other trees in your population are around this, like this, for example, the actual mean may be closer to the case where you remove this outlier when you're computing this X bar. That's why we remove these. Sometimes the outliers are due to some noise in your data. For example, you're computing the running time of your algorithm. Maybe something happened at that time and you got the running time incorrectly. For all the data sets, experiments, you have a running time of 3 seconds, but one of the data points is, for example, 20 seconds. Why is it 20? It may be really the case that your algorithm is working badly. In that case, you shouldn't remove the outlier, but sometimes the outliers may be due to measurement errors. And that may be one reason to remove the outliers before you try to do any processing on this data. But as I said, this is really application and problem specific. Sometimes the outliers are really give you some important data. Sometimes you focus on the outliers that may indicate certain things. If you're doing testing, for example, of your code, that outlier may be a really good indicator of what went wrong with your algorithm, those exceptional cases. Okay, but depending on the application, if you're trying to, like this X bar here, if you try to estimate the population mean, having outliers in your sample may be bad for the population mean. So you may then decide to first filter your data and remove those outliers from that data before conducting any further analysis. But as I said, sometimes we just define those outliers, not the purpose of removing them from our sample, but to just see what's going on here. What are these data points? Why are they so different from the actually 1.5? Here, one thing that is interesting here is that you don't actually just treat the 50% of the population outside Q1 and Q3 as outliers. Otherwise, 50% of your population will be outliers, right? Look at this interquartile range. The interquartile range is the middle point between Q1 and Q3 where 50% of the population resides. Now, if you go one interquartile range, it's like another 50% of the population. I mean, if they were all equally likely distributed, like normally, if they were like uniformly distributed, if you go one interquartile to the left, just one interquartile range to the left of Q1, you should actually arrive, actually there's only, you expect out of 25% of the population, actually the half of, even if they were uniformly distributed, half of interquartile range should get you to the beginning of this population, right? If they were uniformly distributed. Again, half of that interquartile range, you go after Q3, you should end up at the end of that population. But this is really more conservative in the case that when we're defining them as outliers, I don't even go 0.5 IQR. I go 3 times more than that. Let's multiply it with 3, even larger, go way beyond like 75. If they were uniformly distributed, go 75. It's not, I shouldn't go 75 percentile because these are population members, but what I'm saying is that it's like if they were uniformly distributed, it would be like that range will occupy 75 percentile. Why is it 0.5 IQR that I mentioned? Let me try to explain it here. So IQR actually spans 2 quartiles, right? Between Q1 and Q3. The reason this is Q3, this is Q1. The interquartile range itself occupies 50 percentile, right? So Q1 was at 0.25. Q3 is at 0.75, right? So if they were uniformly distributed, how much do I have until I got to Q4, which is the 100th percentile? So the distance between Q3 and Q4 is 0.25, right? But the interquartile range occupies 50 percentile. So it's like, therefore, if they were uniformly distributed, if everything was uniformly distributed, the distance between Q3 and Q4 should be half of IQR, right? Because IQR itself spans the range of 2 quartiles. Is it clear now? So, I mean, if they were uniformly distributed, half of IQR would be the distance between Q3 and Q4, because IQR itself is the distance between two quartiles, Q1 and Q3. It spans 0.5 or 50% of the population. Therefore, if 50% of the population is here, the other half, the other 50%, is distributed this way and this way in half amount. All right, so therefore 25 percentile lives here, 25 percentile is here. When we say Q1 minus 1.5 IQR, we are reaching at a position where whatever this range is, we are reaching in a, by the way, all these numbers, when I say considering they are uniformly distributed, most of the time our data is not uniformly distributed. So there are data points, there are very small data points. They may still be outside in this very long range, depending on, for example, your IQR may be something really small. I mean, imagine, for example, IQR is just 5, okay? And which means that maybe the 50% of the population is between, for example, 75 and 80 kilograms. This is your interquartile range, Q1, Q3, okay? So when I say if IQR is 5 kilograms, when I say 15 kilograms, 1.5 IQR will be 15 kilograms, okay? So when I say Q1 minus 15, I will be reaching out to 60 kilograms, right? So the people less than 60 kilograms will be outlier in this case, if this IQR is really this small. If 50% of the population is between 75 and 80 kilograms, which is not the real case in real life, but I'm just exaggerating here, when IQR, so here maybe the median is 77.5, okay? So if Q1 and Q3 are this, 50% of the population is between 75 and 80, my IQR is 5 kilograms, 1.5 times IQR becomes 15 kilograms, 60 becomes the threshold of Q1 minus 1.5 IQR, and 95 will be the other threshold. In other words, I'm saying if you have data points less than 60, and we may have data points, right? I mean, depending on, it may be, you don't know how the rest of the population, 25% of the population could be distributed in any way in this region. We don't know that it goes uniformly 5 or 25 kilogram, 2.5 kilo, 2.5 kilo. It's not like that. The data, there may be lots of data points here. Half of the population lies here, but there are few points that are, I mean, this is not these interquartile ranges are about like the CDF. It tells you how those data points are distributed. So the 60 and 95 becomes your outlier thresholds. So it's not behind the 0% of the population. So because, as I said, it would be before 0% if they were all uniformly distributed. So there will be no outliers in that case, okay? So what I'm saying is that if you imagine you have some data point that is like this, everything is equally distributed. These are my data points. If these are your data points that are like this, nicely, equally distributed, look at this. If this is your population, there are no outliers, okay? Because in that case, 1.5 IQR and this one, Q1 minus 1.5 IQR, there's no data point there. Since there are no outliers. That will be, in this case, it will be below 0 percentile. But in general, if I have a data that is distributed like this, all the points that are here, okay, interquartile range is really small. What if I have a data point here? Can you say this point is below 0 percentile? No. All right, so this is still this person, how many, this may be in 1 percentile, this outlier, but when IQR is this small, 1.5 IQR may be a point that is here. IQR below Q3 may be something here. And if you have a single data point that is here, that is your outlier. Okay, so it will be, sometimes you may get negative values. That's also possible. It may be the case that if you try to look for outliers, and depending on what this interquartile range is, Q1 minus 1.5 interquartile range may fall into some negative values. If you have weight less than minus negative kilograms, you're an outlier, which means that it's impossible to have an outlier to the left. Maybe our outliers are on the other side. Okay, so it's entirely possible to get this result, whatever you get here for your outlier threshold, to get some values that are absolutely meaningless, like minus 20. Nobody can have minus 20, less than minus 20 kilograms. It's our random variable starts at 0. But if this turns out to be minus 20, that's okay. That's a threshold, which tells you that you will not have outliers in that range. That's also possible. Yeah, so yeah, this quartiles, I think, yeah, the quartiles, they split the population into 4 equal size parts. This is important. Yeah, and the notation usually, this Q1, Q2, Q3, they are the population quartiles and their hat versions. So any one of these things are with hats, they are the estimators of those population parameters. Which we call sample quartiles when we measure these by sorting. When we have, and all of these things are order statistics. The general term for them are order statistics. Oh yeah, yeah, exactly. 1.5 IQR isn't 75 percentile. Otherwise, that's really that's a good point. So when you say compute this 1.5 IQR. It's not 75 percentile. Actually, you add to your 75 percentile this much amount, a large amount. You may go way beyond it. So we don't treat 25% of the population as outliers. If you just use Q3 and Q1 as your outlier thresholds, it means that 50% of the population you name as outliers, because 20% are to the left of this, 25% are to the right of this. You are just saying 50% of your population is outliers. It's not. Q1 and Q3 are not our outlier thresholds. From Q1, before Q1, whatever the range between Q1 and Q3 is, we multiply it by 1.5. We become really conservative, and we go that much below Q1 to name that part as threshold. Exactly. So it's supposed to go. And also, it's not supposed to. Yeah, exactly. So 75. It's not going 75% of Q1. So that range is really depending on something. This range, interquartile range, it doesn't tell us anything about the population, how much of the population is to this side below Q1. It's the interquartile range is only saying something about the middle of the population. Okay, that's the range. 50% of the population lies in the middle. We don't know how it's distributed over there. So it's not, you're not going 75% of the population at this from 0 to 25 quantile range. Okay, so it's possible that sometimes, in most of the cases, there will be no outliers in your sample. Okay, this rule is in such a way that in some cases there are no outliers in your data. It's not like we are always saying, if it's even, this outlier description is even more conservative than this. For example, you may have indicated that any data below 1 percentile and above 99 percentile is an outlier. This is another rule. Look at this rule. Any data below 1 percentile and 99 percentile is an outlier. If I say that, I will always have some guaranteed outliers. So you always have 1%. So you always guarantee to have 2% of your population if you have such an outlier rule. But that's wrong. I mean, they are, if imagine something like this. If all of the population, actually we do something like this when we are having course evaluation, faculty members, they have their course evaluation scores at the end of semesters that are very close to each other. All of them are like, if the out of 5, everybody gets like 4.8, 4.8. Okay, somebody gets, for example, a score of 4.6, doesn't mean it's a bad score, but the way the system works right now is if you are at basically the system tells you that if you are in the 10 percentile in terms of the score, you're a bad teacher. But that's obviously wrong, right? I mean, the statistic that the university administration uses in our university does not talk about. I mean, we should really look at those interquartile ranges and other things. And I mean, if it's close to the population mean, that's 4.6, it shouldn't be considered outlier. If you say 10 percentile, if you're in 10 percentile, you are an outlier. You are teaching badly. It means that you're always going to have that 10%. Imagine those 4.6 is even 4.75, very close to that. All of the faculty members get the same score. You just having a fixed threshold of 10 percentile as your outlier means that even if they are good, you name them as outliers. That's not a good way to determine outliers. We cannot have fixed percentiles for outliers. This is a better rule. At some places, we will have 0 outliers, no outliers at all. And that's fine. It means that the data is really tightly packed, nice distributed, and there are no actual outliers. All right, so we're out of time, and I'm going to continue with this. We have only 10 slides left. We are going to finish this on Tuesday. We are going to look at some example, different how to compute these quartile, percentile, and median by looking at some examples. And we're also going to talk about sample variance and the standard deviation of our estimators. And as I said, we're going to be able to finish this in 1 hour on Tuesday. Yeah, thank you very much. I will stop recording now.